Friends, today we're going to talk about CAN bus. Have you ever wondered how your car's or vehicle's systems communicate with each other? How does your engine, brakes, and dashboard lights all stay in perfect sync? Well, that's exactly what CAN bus makes possible, the hidden language of your vehicle. CAN bus is a reliable communication system used in cars, industrial machines, and EVs. It connects multiple microcontrollers, called nodes, on a shared two-wire bus. Each node can send and receive messages with a unique ID. Lower IDs get higher priority, so critical messages always get through first. The bus uses 120 ohm resistors at each end to prevent signal reflection and ensure clean communication. Nodes listen before sending, resolve conflicts automatically through arbitration, and acknowledge received messages. This makes CAN bus fast, robust, and perfect for real-time control systems.
Let's look at how CAN bus communication works inside an electric vehicle or battery system. If we have an STM32 microcontroller-based node, or PCB, the STM32 does not connect directly to the CAN bus. Instead, it communicates through a CAN transceiver, which converts digital signals into robust differential signals called CAN high and CAN low. All system nodes, such as the battery management system, motor controller, DC to DC converter, and dashboard, are connected to the same twisted pair cable. Termination resistors at both ends of the bus ensure signal stability and reliability, even in electrically noisy environments. In the illustration, feel free to pause, we see a high-level CAN message structure. Each CAN message contains an identifier, which defines the message priority and meaning, followed by a data length code and up to 8 bytes of actual data. In a BMS example, these data bytes can represent battery voltage, current, state of charge, temperature, and fault information. Error checking and acknowledgement are handled automatically by the CAN protocol. The key takeaway is that CAN messages describe what the data represents, not which device sent it. This design makes CAN bus deterministic, scalable, and ideal for safety-critical electric vehicle systems. Every CAN message begins with a start of frame bit. This bit synchronizes all nodes on the bus and aligns their internal clocks before data transmission begins. Next comes the arbitration field, which contains the message identifier and determines priority on the bus. Lower identifier values always win arbitration, ensuring that safety-critical messages are transmitted first. The control field follows and includes the data length code, which tells all receiving nodes how many data bytes to expect. Only after timing, arbitration, and control are established does the actual payload data appear. These data bytes carry information such as battery voltage, current, state of charge, and fault flags. After the data field, the CAN hardware appends a cyclic redundancy check. All receiving nodes independently verify this CRC, acknowledge valid messages, and automatically request retransmission if an error is detected. This strict bit-level structure is what makes CAN deterministic, synchronized, and safe for electric vehicle and battery management systems. And now let's look at the main types of CAN bus used in automotive and industrial systems. These are commonly categorized as CAN A, CAN B, and CAN C based on speed and criticality. In newer systems, we also have CAN FD and the latest evolution, CAN XL, which extend CAN's capabilities for modern vehicles. CAN A is the low-speed version of CAN bus. It typically operates at speeds up to 125 kilobits per second. CAN A is used for non-critical body electronics where timing is not safety sensitive. Typical applications include window controls, seat adjustment, interior lighting, climate control panels, and door modules. The key advantage of CAN A is robustness and cost efficiency rather than speed. CAN B operates at medium speeds, usually between 125 and 500 kilobits per second. It is commonly used for systems that require more frequent updates, but are still not strictly real-time safety critical. Typical applications include instrument clusters, diagnostics, infotainment coordination, and gateway communication between different vehicle networks. CAN B acts as a bridge between comfort systems and higher speed control networks. CAN C is the high-speed CAN bus used for real-time and safety-critical systems. It operates at speeds up to 1 megabit per second. CAN C is used in powertrain and vehicle control systems, where deterministic timing is essential. Typical applications include engine control units, motor controllers, battery management systems, braking systems, and torque commands. In electric vehicles, CAN C is the primary backbone for drivetrain and energy management communication. CAN FD, which stands for Flexible Data Rate, is an extension of classical CAN. It keeps the same arbitration and reliability mechanisms, but allows much higher data throughput. CAN FD supports payloads up to 64 bytes and data phase speeds, typically between 2 and 8 megabits per second. CAN FD is widely used for advanced diagnostics, over-the-air updates, high-resolution sensor data, and modern EV subsystems. It allows more data to be transferred without increasing bus load or complexity. CAN XL. CAN XL is the next generation of CAN, designed to support future vehicle architectures. It supports payloads of over 2,000 bytes and data rates exceeding 10 megabits per second. CAN XL is intended to coexist with Ethernet in software-defined vehicles while retaining CAN's reliability and deterministic behavior. Typical applications include zonal controllers, centralized vehicle computers, and high-bandwidth control data. CAN XL represents the evolution of CAN into the era of intelligent and highly connected vehicles. In summary, CAN A, B, and C divide CAN by speed and criticality, while CAN FD and CAN XL extend CAN to meet modern data demands. That concludes today's session. Feel free to ask any questions in the comments. Until next